Good morning, students. Today we will discuss the examples of neighborhood system of a point in a topological space. So first of all, we define neighborhood of a point. So let us take X with topology top be a topological space, and let us take a point X belonging to the set X and a subset W of the set X. Then we say that this W is neighborhood of the point X if there exists an open set G such that X belongs to G is contained in W. So if this condition is satisfied, we say that W is neighborhood of the point X, and the collection of all the neighborhoods of the point X, that is called neighborhood system of the point X. Now let us discuss the examples of neighborhood system in various topological spaces. So first of all, we consider the example of usual topological space, means the set of real numbers with usual topology. We will work out for the neighborhoods of points of set R. Now, if we take any subset of R, then by definition A will be the neighborhood of point X of the set R if it contains an open interval containing the point X. It means X belongs to R and A is subset of R. Then A will be neighborhood of the point X. It means there exists an open interval AB such that X belongs to this open interval is contained in A. So we can say that neighborhoods of point X on the real line with usual topology are the supersets of the open intervals. Now, our next example is the set X together with the topology induced by the metric D on the set X. We will work out for the neighborhoods of point X belonging to the set X. Let us take A be any subset of X. Then A will be neighborhood of this point X if there exists a positive number R such that X belongs to the sphere with center X, radius R, and this sphere should be contained in A. So we can say that the neighborhoods are the supersets of open sets, and here the open sets are formed by the open spheres. So we can say that the neighborhoods are supersets of open spheres. Our next example is in discrete topological space. We will work out for the neighborhoods of a point in this topological space. So let us take the set X together with in discrete topology tau1. This topology consists of only two members, the set phi and the set X. So if we take a point X belonging to set X, then X is the only neighborhood of the point X. It means the neighborhood system of this point X consists of only one member, which is the set X, because in this topology X is the only open set containing the point X. Now, our next example is discrete topological space. The set X together with the topology tau2. This topology is the collection of all the subsets of X. It means this topology denotes the power set of X. Let us take point X belonging to the set X. Now we'll find the neighborhood system of this point X in this topological space. Let us take W be any subset of X. Now because W is subset of X, so by definition of discrete topology, that will be open in this topology. So if X belongs to W, then W will become neighborhood of the point X. So we can say that every neighborhood W of the point X, that will be a member of neighborhood system. So the neighborhood system of the point X is the collection of all those subsets of X which contains the point W, which contains the point X. Our next example is co-finite topological space. The set X with the topology tau3. This is co-finite topological space. By definition, co-finite topology is the collection of all those subsets of X which are either empty or their complement is finite. This topology is denoted by the topology tau3. Now let us take a point X belonging to the set X. We will work out for the neighborhood system of this point X. Let us take W be any subset of X. If W is neighborhood of the point X, then by definition of neighborhood, there will exist a member G from the topology tau3 such that X belongs to G is contained in W. Now, because G belongs to tau3 and X belongs to G, so X belongs to G implies that G is non-empty. Now because G belongs to tau3, so either G should be empty or its complement should be finite. But G is non-empty, so its complement will be finite. Now, because G is contained in W, taking complements on both sides, we get complement of W is contained in complement of G. Now complement of G is finite and subset of finite set is again finite. So complement of W is finite. And by definition of co-finite topology, W belongs to tau3. So W is open. It means every neighborhood of the point X turns out to be the open set W which is in tau3. So we can say that every neighborhood turns out to be a member of topology tau3. Our next example is co-countable topological space. The set X with the topology tau4. Tau4 is co-countable topology. And by definition, this topology consists of all those subsets of X which are either empty or their complement is countable. We will work out for the neighborhoods of a point X in this topology. So let us take a point X belonging to the set X and W be any subset of X. If we consider W to be neighborhood of this point X, then by definition of neighborhood, there will exist an open set G such that X belongs to G is contained in W. Now because G is a member of co-countable topology, so either G should be empty or its complement should be countable. Because X belongs to G, so G is non-empty, so its complement should be countable. Complement of G is X minus G. So X minus G is countable. Now G is contained in W. Taking complements on both sides, we get complement of W is contained in complement of G. Complement of G is countable and subset of countable set is again countable. So we can say that X minus W is countable. So by definition of co-countable topology, the set W belongs to the topology tau4 and therefore W is open. So we can say that every neighborhood turns out to be open in topology top 4. So these were some of the examples of neighborhood system of a point in a topological space.